Okay, we're live. Yeah, everybody good? Hi, so we're back on this week's Data Science Deployed. We have Donny. Say
Hello.
hi.
Hello.
Ben,
Hello.
and me, Jillian. And with us this week, we have Greg Wilson, who's going to talk to us about software engineering around data science, I guess. Or I'm sure you can give a much better introduction yourself. So why don't you introduce us, Greg?
Sure. I'm Greg Wilson. I'm currently in Toronto. I'm about to start a new job with a company called Deep Genomics that is doing machine learning applied to drug discovery and targeted therapies. I'm probably best known in the data science community as the co-founder of Software Carpentry. And I believe Donnie's heard the story of how it came to be, but since most of your listeners won't, back in the late 80s, early 90s, I was working at what is now the Edinburgh Parallel Computing Center. I was the first professional programmer hired by the group that eventually became EPCC. And my job was to take whatever code the scientists had and make it run a gajillion times faster on the parallel supercomputer in the basement. Right? So one day, the new hire in astronomy comes in with his 100,000 lines of Fortran that represents a decade of his life and says, I hear you can make this run faster, that would be good. It's all in one file, but when I open the file, at least there are functions. It's not one great big block of Fortran, there are functions. And I feel this sense of relief, which lasts until lunchtime, which is how long it takes me to realize that all the functions down in the bottom of the file are the bits of code he's no longer using. His simulation is the top half of the file. Every time he makes a significant change, he carves out a chunk, puts it in a function with a meaningful name because he's been taught that that's important, and then he doesn't call the function. He's using functions for version control because nobody had ever shown him that there was a better way. And when I started looking at this, I realized that I could do things over a coffee break that would take many of my colleagues in physics and geology and astronomy a day or a week. And it absolutely wasn't because I was smarter. It was because somebody had shown me that there's a tool. This is a solved problem. And over again, I saw us as a community assuming that everybody who wanted to do computational work could essentially do the equivalent of reinventing calculus from scratch. Right? We teach people the math that we have and the science that we have so they can build on top of it. And at the time, nobody that I could find was teaching scientists things like, how do you test a piece of code? So they were either not doing it, or they were doing it the hard way, or they were wasting months or even years building their own tools that didn't build on previous experience. And that's just unfair. It's unfair to ask somebody to recapitulate 30, 40, 50 years of development and get a PhD on top of that. So Brent Gorda and I started teaching workshops at Los Alamos National Laboratory and then at some of the other national labs and a few other institutes. That's how I met Donny. It was an on-again, off-again project for several years. And finally in 2010, I left a faculty position at the University of Toronto and devoted myself to it full time for a few years. And I think it was a case of being in the right place at the right time. You know, there's that old joke about how a band will work for 10 years to become an overnight success. And we had the material, we had field tested the material, we'd made a lot of mistakes, but we finally had the right curriculum and the right way to deliver it at a time when the rest of the community had sort of woken up to the fact that if it isn't open, it isn't really science. If I can't get your data and your code and check things, then I'm just taking a lot on faith. And I should apologize for putting it that way, because I have had many people get quite upset at the implication that they're not doing real science because they're not doing this new thing. And I don't mean to imply that, but with so much of our work now computational, a little bit of computational competence is now just an accepted need. And whether it was focused around reproducible research or around open access to data, to publications and so forth, there was now finally an audience for what we had been talking about all these years. And it grew pretty quickly. the core curriculum continued to focus on the basics because that's where there was the most need. But I've always wanted to go back and add that next layer. So you're already breaking your code up into functions, and God help you, you're using Git, which is probably the least pleasant piece of software I've ever had to teach. And I've taught people Emacs, so the bar here is pretty low, right? But you've got all of this, and the question is, what next? Do you need to know Docker? I'm still on the fence about that, but you do need to know how to use a logging library, because eventually your package is going to be plugged into a pipeline with 15 others, and somebody who hasn't written it is going to have to be able to tell, is this healthy or not? Is it still working? Has it complained? And if all you're doing is printing messages to the console, that's not going to help them. The issue of data provenance is still, for me, unsolved. There was a flurry of interest 15 years ago. There's an open provenance standard that nobody knows about and nobody pays attention to. And we still don't have effective ways to track a result back and say which data sets and which code produce this next year or 5 years from now. And every few months, a story will bubble up about a data set that was either incorrect or fabricated or had been fixed. And we have no idea how many people downstream are affected by that. And that's going to bite us one of these days. Probably already has, and we just don't know it yet. So there's a whole bunch of operational issues that I think the community is now ready to start tackling. Morgan Tashik leads a team at the Ontario Institute for Cancer Research, and in 2017, she and I put out a paper that's the rules her group has put together for building robust software, because their team's job is to take what the postdoc got working on her laptop for her data set and turn it into something that you can deploy on a cluster next year halfway around the world, and it'll work reliably on somebody else's data set. And the difference between those is something I'm really interested in these days. It's great that we have more people using computational notebooks, using version control. It'd be great if those two things worked better together, but that's a rant for another day. But given how reliant science is now on the assembly of these things and having them run in pipelines, there's another skill gap there, and we need to fill it in. So it's probably a longer answer than you were looking for. I apologize for that.
Oh no, we're looking for all the answers. Yeah, I think that's really interesting because you and I both come from an HPC background, so I always like talking to my fellow HPC people. So if people do want to go and learn about, say I'm a data scientist and I have data and I care about this data, I care about this research that I'm doing, which I would say most researchers do. What are some kind of top tips that people can go and learn about, and where can they learn them? And give us the whole rundown here.
Sure. A group of us spent a couple of years writing a book about exactly this, and I think it was its publication is what prompted Donny to get in touch with me. And you can throw a link in to the website, but we've got a book that's research software engineering with Python, and it assumes that you already know enough Python to write programs that are a few hundred lines long that are broken up into functions and so forth. And the question is, what do you do next? I think everybody needs to know enough about the Unix shell to write simple scripts that glue things together. I always have to look up the syntax for writing an if statement in a shell, and if I get far enough that I need to write conditionals in a shell script, it's time for me to switch and do it in Python. Right? But if what I need to do is run these 5 programs in this order and connect the data in the following way with the following parameters, I want that in text so that I can save it, review it later, hand it on to somebody else. I really wish one of the alternatives to Make had gained enough traction to be an obvious successor. There are hundreds, literally hundreds of build tools out there, and none of them has more than a tiny percent of the total user base. People keep using Make for the same reason that a lot of scientific code is still written in Fortran and a lot of papers are still written in LaTeX. It sucks, but it's what everybody else is using, and nobody's come up with something that is so clearly better that the community is willing to shift. But we desperately need a better build management tool. And just yesterday, I was reviewing a wonderful paper by Mochov and colleagues from the UK, where they came up with a taxonomy of different build tools and then did a rational reconstruction of several different ones as variations on the theme. They said there's a core idea here, but there's a couple of places where build systems make different decisions about how you tell what is out of date, in what order do you rebuild things, and so forth. And we can make those pluggable modules so that we can experiment with the design trade-offs. And I hope that work like that will eventually lead to something that is a 21st century replacement for Make, because that's an absolutely essential tool. I'm a lone voice crying in the wilderness about logging tools, but as a former sysadmin and as somebody who's had to babysit large data pipelines, please, for the love of all you hold holy, go and get a logging library. They exist in every language we use. Plug it in and use that instead of print statements to tell me what's going on. Because I do not want to have to pipe standard output from a 95-stage pipeline into a text file to grep ever again in my life. Like, I just don't want to do this, and everybody's life will be better if you use the Python logging library or its equivalent in R or MATLAB or Java or C++ or whatever other language you have. And this technology is 25 years old, people. Please don't make me cry. Right? The other two big unsolved problems, unsolved is probably too strong. The other two problems where I'm unhappy with the solutions we have to offer data scientists are package management and testing. Package management is hard for everybody, and what makes it hard is the package managers don't handle cross-language dependencies cleanly. Conda does an okay job. The R ecosystem does an okay job, but when you're trying to synchronize several R packages with a couple of Python packages, and they have native interfaces to underlying libraries, and you've got to get all of that working on a machine. And the package management tools don't know how to talk to each other. You wind up in this infinite regression where the Python module changes the C library, so you have to recompile the R, which changes some other C library, so now you have to go back and recompile the Python. And I'm seeing heads nod. The audience obviously can't because it's a podcast, but this should not be necessary. Right? There was a point in time in the early 1990s, in the early days of Red Hat actually, when there was a very real chance that we could have wound up with one cross-language package manager. It didn't happen for a whole bunch of accidental reasons, but our lives would be a lot better today if package management was a single solution problem, in the same way that version control is now essentially answered by Git. And yeah, Git's horrible. You don't have to take my word for that. The work of Perez de Rosso and Jackson at MIT about 7 years ago showed that even expert users have a very different mental model of how Git actually works than it actually works. And every single one of those mismatches is an incomprehensible error, a detached head, and an evening in the bar drowning your sorrows. And I think Mercurial is proof that it didn't have to be that hard, but again, because of historical accidents, Git won, and we just have to deal with it. The other problem, and the other place where I wish we had better solutions, is testing. There used to be a module on testing in the software carpentry curriculum, and after a couple of years, we took it out because all we were doing was frustrating the scientists. The conversation goes something like this. Hi, I'm a software engineer. Let me show you how to write unit tests and run them using this unit testing framework. To which the scientist replies, gosh, that's wonderful. That will be very helpful. What tests should I write for my simulation of rapidly rotating, highly magnetized black holes? The software engineer says, I have no idea. And the scientist says, well, to tell you the truth, neither do I. Because if I knew what the right answer was, I would already have published and moved on. And if we go back to the work of people like Les Hatton in the 1990s, we find that there is an inverse correlation between where the bugs are in the code and which parts of the code the unit tests exercise. Now, it seems like this is obviously true. The more you test, the fewer bugs you will have there. But what was found was that scientists didn't even write the tests for the most complicated and most error-prone parts of the code because they were hardest to test. They would test the file parser because I know how to do that. They wouldn't write the tests for the highly magnetized, rotating, whatever it was I said a few moments ago, because what do you write?
Yeah, how would you even write that test? Yeah.
Right? If there is a closed form solution so that you can tell what the right answer is, you didn't write the code. If you simplify the problem enough that you can work it through in some other way, you're not exercising the tricky code paths that are most likely to give you bugs. Jonathan Dursey, who is also here in Toronto, says the difference between commercial code and scientific code is that commercial code is complex, scientific code is subtle. You might have a piece of code that is just one great big straight line computation with a few parameters whose values have to be fairly precisely set. So the toolbox that I have as a software engineer for testing things like apps on phones doesn't tackle the problems that scientists actually have. And there's an old joke, it isn't particularly funny, but at least it's old, that physicists worry about decimal places, astronomers worry about the exponent, and economists are happy if they've got the sign right. But what that shows is that every scientific field has these unspoken community agreements about how close is close enough. Like when I trained as an engineer 40 years ago, nobody told me that you get 3 significant digits out of a desktop voltmeter. But when I'm in the lab, that's what I'm seeing other people do. That's what the lab tech is doing during the demo. 4.75 plus or minus 0.02 volts. So nobody told me that's how accurate it needed to be. I just soaked that up. Geologists, ecologists, every field that does quantitative has these community agreements that are almost never written down. It's just, how do we do this? Every field has its error bars, and we don't have those for computational work. And when we even try to think about it, we immediately fall into the trap of trying to do precise numerical analysis and think about it as a floating point roundoff problem, and it's not. I mean, yes, there are problems with floating point roundoff. But again, going back to some of Hatton's work in the 1990s, looking at various geophysics codes, you're likely to get one significant digit of agreement out between different codes because of the different assumptions about backscatter. And it's not a problem with numerical precision, it's a problem with the science. In the same way that if 3 different astronomers measure the Hubble constant 3 different ways, they're going to get 3 different values. We expect that. And now we get to argue over which one is the most accurate value and how do we reconcile these and how do we do better experiments. And computational work is not that mature yet. And as a result, I don't know how to tell you what error bars to put on the checks in your unit tests, which means your unit, it's just not worth writing the unit tests. And I really wish that this, rather than petascale computing, machine learning, and anything with cloud and blockchain in the title, were what we were focused on right now.
I think that's such an interesting point because so much of my work has been kind of around this idea of we have the scientists over here and the software and the IT people over here, and we have to get them to talk to each other. And I found like the biggest kind of problems or miscommunications, or the most interesting problems for me anyways, are these problems where the scientists sit down and write some code, and there's this whole group of just kind of assumed knowledge and background that they have about this particular data set because they've been studying it for likely decades, yep. That the software people just don't have, and so you end up with all these kind of disconnects, and the software engineers think one thing is the priority and the scientists think something else is the priority, and you can go back and forth on that. Do you have any kind of ideas in tackling that?
So Marion Petrie and I did a study in 2014 where we got some very experienced software engineers from Mozilla to do code reviews on scientific code. And the conclusion was that it's not useful, because if you don't have the deep domain knowledge that somebody with a graduate degree in a scientific discipline has, you can't understand or critique the deep issues in the code, the algorithmic issues, the subtleties. You can talk about indentation and variable name, and maybe this function's getting too long. There's a lot of superficial stuff. I don't know whether you've ever shopped for a home, but people fall into two very distinct categories. There are the people who come and look around and say, oh, I don't like the color of the walls, right? Not thinking that that is a day and a few $100s to fix. There are other people who come in and say, all right, that wall's in the wrong place, and let me take a look at the foundations to see if there's any cracking in the concrete, right? The useful collaboration comes when you can have that latter discussion, but you need the deep domain knowledge. And one of the reasons that the carpentries exist is that you can teach a scientist enough about programming in a couple of days to make a real difference to their productivity, or at least to their self-confidence. You cannot teach somebody enough about metagenomics in 2 days for them to be able to collaborate with somebody who's doing leading edge research in that field. And it would be unreasonable to expect otherwise. So right now, I think what we have to do is what the research software engineering community in the UK has pioneered, which is recognize and foster the scientists who are picking up the coding skills to support their fellow scientists. I mean, the biggest development in open science for me in the last 20 years is the institutionalization of research software engineering in the British academic system. The fact that you can now have a career, that there's a job category with a progression, that you don't have to keep explaining to grant committees, what is this person for? So that there's a decent chance they will actually stay in the research system rather than going out into industry because they keep getting passed over for promotion, they're always on soft money and so forth. That is the single biggest, that matters more than anything with the word cloud in its name, because that's a systemic change. And I really hope we can see similar successes at the institutional level in the United States and in other jurisdictions. There isn't a research software, I just discovered last week, there is not a research software engineers association in Canada yet, because you're not allowed to call yourself an engineer, right? I trained as an engineer, and the professional association in Canada guards the term engineer very, very carefully, right? In the same way that terms like medical doctor are guarded and regulated very carefully. And so the big stumbling block is just, what would we call this? But if we can get past that and get people recognition and job security and a chance to get promoted through the ranks so that 10 years from now, they're the ones signing off on grants. They're the ones deciding how effort is going to be allocated. That's a much better world than the one we have right now.
That's so interesting that you bring that up, because I never quite thought of it like that. But now that I'm thinking of it, you know, you're right. For the computational people within like academic research, that's where I was for 10 years. There really is no career path. So most of us tend to top out. You know, I mean, it's you know, it's a great experience. It's wonderful to be there. I was there when I had really young kids, and that was, you know, and that was fantastic because it's a very nice environment for that kind of thing. But at some point, your career just tops out. Whereas yep. I found it was completely the opposite case for the scientists who wanted to learn some computational skills, because I spent quite a bit of time with them. Like the scientists, the biologists who were willing to learn, at least able, you know, to be able to run their analyses on the HPC. Like the sky was the limit for them in terms of career
yep.
projection.
And many fields have had this problem and solved it. For example, the people building the LHC weren't doing physics in the sense of discovering new particles. They were making it possible for everybody else to do that. And they were recognized and valued for that. They had to know a lot of physics to build the collider, to build the detectors, right? But everybody accepts that their goal is to support other researchers. The people building the next generation of telescopes have to know a lot of astronomy, but they're not actually doing astronomy. They're not actually, most of them, looking at the stars. They're making it possible for other astronomers to look at stars. And those other astronomers recognize that contribution value. You can get promoted. You can get to be chair of a department or get a position on the NSF as a telescope builder because your field has accepted that without that, we just stop. There isn't anywhere near the same recognition of software builders. Right? I mean, there are a few small, low-impact journals devoted to scientific software, but that's not prestigious. Now, I am looking forward to a day when a journal like Nature routinely includes an article or two in every issue about advances in the tooling, in the same way that when polymerase chain reaction was developed, they devoted articles to that. It's not biology, it's a tool for doing biology, but man, that's a good tool, right? And its value is recognized. I mean, you get a Nobel Prize for inventing a good tool in biology. You can't even get tenure for inventing software that's used by a million people. Go ask Travis Oliphant. NumPy wasn't considered worthy. Since we're on the topic, back when I was faculty at the University of Toronto, I actually taught a semester-long version of software carpentry to grad students several times. It was offered as a grad level CS course. Enrollment was about 2/3 non-computer science, about 1/3 computer science, and most of those from CS had done their undergrad in other disciplines. They'd come in from math or physics and just didn't have the technical skills. And after a couple of runs of this highly rated and oversubscribed course, the graduate curriculum committee decided that it just wasn't going to be offered again. And I couldn't get a straight answer as to why. It was finally at a departmental Christmas party, I cornered one of the faculty on that committee who'd had a couple of glasses of wine. And he said, well, yes, Gregory, we realize that it's very popular, but it is merely useful. And that's a phrase I've used over and over again. Now, I understand his point of view. Don't get me wrong. I think it's a valid one. I was not doing the science of computing. Right? There was no theory in what I was doing. There was no advance in human knowledge directly from what I was doing. I was doing the equivalent of teaching people good lab skills. And that is typically done at the undergraduate level. However, in many science disciplines, you go into grad school, I think about biology, right? A large chunk of your first couple of years of grad school in cellular biology is learning how to work in a wet lab. Because if you don't have the technical skills, you can't do the science. Learning how to set up interferometers, learning how to do a C12 analysis is really hard. And it's accepted in those disciplines that at the graduate level, we've got to put time into learning how to do this, right? There is no similar acceptance that computational work requires similar investment, that it needs to be part of the curriculum, that it needs to be rewarded and accounted for. It's just supposed to magically happen. Right? And clearly that model is not working. So I've said this before, it's not really a secret. The long-term goal with the carpentries was to create a generation who would then age up to the point that they were sitting on curriculum committees, that they were department chairs, and they could make the changes that we couldn't. There weren't enough people who understood the problem in 2010 to get any substantive change. All right, let's take a 20-year solution. Let's teach people who are grad students and postdocs and junior faculty then, and then wait 15 years for them to be on NSF and NIH committees. And then they can start putting things into, RFPs. right? And we're starting to see that kind of shift. 20 years ago, people like Phil Bourne were laughed at for suggesting that you could run an open access journal that would be sustainable and high impact. PLOS has changed the world, and Sci-Hub has changed it even more. Right? Like we're slowly winning these fights. I have not yet seen somebody have a grant pulled because they hadn't demonstrated that their code and data had been archived in a reproducible way, but that day is coming. Right? It's just the future takes a long time.
I'm wondering what kind of infrastructure you think needs to be in place. I mean, we kind of touched on career progression. I guess I'm just feeling a little bit lost because for myself, I'm really not seeing this. I think maybe because I've been mostly in the U.S. and the research engineers that I've worked with have all kind of aged or careered out at some point, where most of them have switched to industry because there wasn't that career progression. So from my purely anecdotal experience here, I'm just sitting here saying, who do I know that would eventually get to like one of these really top tier positions where they're writing grants or they're making papers or anything, anything kind of on that level? And I don't think I've seen that. Is it different in the UK maybe?
The ones that I know are getting promotion for the research output and spending most of their time on the computational tools that enable that research output. Right? And I could rattle through a bunch of labs where most of the work goes into building the software, which is then used to crank out a series of papers on, everything from chicken genomics to nuclear fuel cycles, right? And it's a bit of a risky game because if the software doesn't come together in those first 2, 3, 4 years, you're left with nothing. But the same is true of a lot of field work in science. You don't have to go very far to find horror stories in fields like geology, where they went and looked and there wasn't anything in that patch of ground novel enough to be published, right? It's a risk. Personally, I think part of the solution to that is to be a little more welcoming of negative results in publication, but that's a rant for another time, right? I also think that Darwinism is going to solve some of this for us. Places like Germany, the Netherlands, the Scandinavian countries, the UK, where they do have strong research software engineering societies, have got a competitive advantage when it comes to doing novel science. And I don't think other countries are going to let themselves be scooped indefinitely. Sooner or later, somebody says, why are all of the papers in this field coming from somewhere else? Right? The problem is that kind of realization is a decade-long thing. And going back to the 90s and the early 2000s, I thought this would be fixed quickly. A year, a couple of years. The truth is obvious. They will believe. The church will grow, right? Yeah, no, didn't happen like that. I think we've got a lot of technical infrastructure. I think there is grossly unequal access to it. In theory, fiber optic means that you can be in the middle of Saskatchewan or the middle of North Dakota and you're on a level playing field with people who are at Harvard and Stanford and the other overprivileged institutions. In practice, no, it is simply not true. And that's even within North America. When I talk to colleagues, particularly in Latin America, about the inequities they face, it's just much, much harder for them to play the game for dozens of reasons. So, William Gibson said that the future's already here, it's just unevenly distributed. I think the same is particularly true of scientific computing. We've got all the future we need, we just need to share a little better. And I didn't think this at the time, but looking back, one of the reasons to focus on skill training is it transports easily. you can take it to that school in Saskatchewan or North Dakota or rural Argentina. Right? It's much more portable than an HPC facility or access to an HPC facility. It's a good way to level up, play smarter rather than play richer. And I think that's one of the reasons why things like the Carpentries and Our Ladies, other organizations have grown so explosively in sub-Saharan Africa and Latin America, is it's a way to level up through effort rather than expenditure. And I'm happy to see that. It's still grossly unfair, but it's a path forward. Technical infrastructure, honestly, I don't know. I think we have in Python and R, we have two mature, usable data science ecosystems. I don't think we need a third right now. I know lots of people are touting other languages. Honestly, as I said at the start of this podcast, I'm just not interested any longer because I don't think we know enough yet to do the next one better. I want a better package management solution that works across multiple languages and across multiple operating systems. I like Homebrew. I can't use it on Windows, and I use Windows frequently.
I have a question about that. You talked about package management systems a little earlier. You also asked whether we need Docker. So you're not sure about Docker. Maybe it's not an elegant solution to package management, but what about doing your development in Docker on your local machine and sort of using that as the composable unit?
I've heard a lot of people pushing this. There's a group in the UK that has spent much of the last 10 years building tools to get data out of old PDFs. And I am confident that 10 years from now, there will be a similar group trying to get data out of old Docker images, right? It is not a solution to the reproducibility problem, except in the small, right? When my daughter cleans their room, they put everything in a box, put the lid on the box, and put the box in the basement. Okay, that is not the same as organizing your room.
Totally true.
That is the Docker approach.
Yeah,
right?
yeah. It's also a pragmatic issue. I think it does not make everything reproducible. I agree. It does not organize your code, but it does solve the problem of I can't run the same thing on Mac and Windows.
I regard Docker as essentially an admission of defeat. We couldn't be arsed to solve the package management problem, so let's just give you another operating system.
Yep, exactly.
Right? And let's require you to turn everything into a microservice, because even with Docker, we can't get these three modules installed in the same image. So slap a REST API on them and build this complicated and undebuggable system of communicating microservices.
Yeah,
and
that's
claim
true.
that that's a solution. I realize this is a podcast about data science deployed, not data science sarcasm, but bloody hell, people, we're supposed to be the smart ones.
Yeah, I think that's a very good point. That this is not actually an underlying solution to the problem, and you say it's undebuggable if you go into a microservice, and I agree with that. But I think also you talked about the most interesting part of the code is untestable anyway, or you can't put it into unit tests.
I can't write unit tests is not the same as untestable.
I'm curious if you could talk more about that. So how do you verify your result if you don't know the solution yet?
There are several techniques you can use. Validation against lab results is the gold standard, and I think that most scientists do that when and where they can. Now, obviously, rapidly rotating, highly magnetized black holes don't have one of those in the lab, right? But there's a lot of other situations where we can backcast against historical data, where we can, I love cases where people have done the prediction and then gone and done the physical experiment to check it so that the coding isn't biased towards a pre-existing result, right? That's science. We would accept that. I really like the approach that climatologists have been taking which is to compare the models against one another. Right? Sometimes they discover simple coding bugs, sometimes they discover algorithmic bugs. Often what they uncover is different assumptions, but they put in the hard work to go backwards and say, why are these predictions different? Right? And at that point, they can have an argument about the science. How does thermal transport work in adiabatic environments? Okay, great. I disagree with your assumptions. Let's go off and have a science argument. That's great. It isn't practical in most fields because most fields don't have that many independent teams working in them. Right? But on the other hand, I regard this as another symptom of the systemic lack of support. If computational work was supported properly, there would be more cases where there are two or more teams working on the same important problem at the same time who can validate the results or at least compare the results against one another. The reason it doesn't happen is, number one, scientists tend to pick on important problems that are easily publishable because that's the incentives they've been given. And number two, there just isn't enough money in the system to fund two teams on anything that isn't regarded as a national scale priority. Okay, those are both fixable. And I think that's the way forward, in the same way that astronomers using multiple techniques to get the Hubble constant and then arguing over why these values are different. Is the universe younger than we thought? Is dark energy a stronger force than your model accounts for? Do we need better optical correction on the telescopes? Are our models of Cepheid variables wrong? Great, now we can go and have that argument.
Yeah, that's really interesting. I think the other question that comes to mind is, you've talked a lot about sort of broad scale challenges in the entire system. I'm curious what advice you give to young scientists, software engineers who care about this space, who want to make an impact.
All right. Short answer is I'm running a workshop next week, and we'll probably run it again several times in the coming year, which is about leading and managing research software projects. Of the 8 hours in that workshop, only about an hour and a half is spent on technology. Because the hard problems are, how do you get people to know that your research even exists? Researchers regard marketing as a dirty word, but it's not. Right? As we've seen throughout COVID, scientists have done a lousy job of conveying what they know to the general public. And as a result, the general public doesn't pay attention and people die. We have to be better at this. Whether it is pandemics or climate change or a host of other issues, right? We really suck. I mean, if a talk show radio host who didn't finish high school can have an audience of 5 million, you'd think somebody with a Nobel Prize would be smart enough to get an audience of 1,000, right? So that for me is something that I would tell anybody embarking on a career in science. Alan Alda, the actor, founded an institute that teaches science communication skills. You can look it up online, the Alda Institute. Go do one of their workshops. Learn how to tell people why this stuff matters, why they should pay attention, because you will literally be saving lives. The most popular lecture I give these days is how to run a meeting, because that's another skill that data scientists and other scientists need as soon as they start working in the large. We particularly in a situation where you've got a distributed team of volunteers. You think about, for example, the SciPy community. At a guess, the major contributors to SciPy work for 50 different institutions. That's probably an underestimate. Okay, so command and control structures simply don't work in that environment, but we need to use people's time efficiently, because otherwise, A, we're wasting time, and B, because we're wasting time, they're going to stop contributing. Okay, so learning how to run a meeting, learning how to do open source project governance, these are absolutely crucial skills for somebody who's a junior researcher, because they're not going to get to be a senior researcher unless they're very lucky, work very hard, and master some of these skills. The good news is you don't have to be very good to be better than most academics, right?
That might be too low of a bar. I don't know that we can go with that one.
But that means there's lots of potential for growth, right?
A lot of good opportunities.
And again, the irony is that, I mean, you've all done graduate work, right? First thing you get taught, when told to do when you pick a topic, is go look at the literature. What's been done before? Do the reading. And then we start running teams, and again, we're expected to reinvent it all from scratch, or by watching our supervisor who wasn't taught how to do this either. We know so much as a species about how to work together efficiently and how to manage people who are deliberately inefficient, that there's no excuse for not doing this better. I'm not even asking for us to do it well at this point. You know, I just want better. And it's not hard. Carl Fogel's book, Producing Open Source Software, all of which is free to read online at producingoss.com, gathers together almost 30 years of experience. And I drew on that a lot when putting together the material for managing research software projects. Again, he spends about a quarter of that book talking about the technology, because there is a standard model these days. You've got a build system. You've got continuous integration. You can rerun tests and you've got coverage. You've got a single command that will build a package. You've got an installer. You've got, there's a bunch of things that we know we need to have now, and there are workable tools for all of them. Some of them are a bit creaky, but we don't need to invent anything new there. We pick the pieces and assemble them, right? The rest of the book is about the stuff where most people in open science have huge knowledge gaps. I don't know if any of you have ever had to fire somebody. Okay, yeah, okay, that's difficult. Okay, first time I fired somebody, the rest of the team stood up and applauded as I marched him out because he was a jerk. Second time, word came down that every team had to shed 20% of headcount because finance, right? So I had to pick one of the 5 guys working for me and say, you've been working your ass off, you're doing great stuff, you no longer have a job here. And it really hurt. And it hurt more than it needed to, because nobody had trained me or taught me how to do this, right? And that's not only unfair, it's inefficient and damaging. One of the more popular articles on my blog is what to do when you've been fired. As I think some of your listeners will know, I used to work at a company called DataCamp. Their CEO sexually assaulted one of my colleagues. The company was trying to cover it up. 2 of us were fired in the summer of 2018. BuzzFeed has an article if you want the details. I think I handled that reasonably well because I'd been through that before. But I have seen people make a real mess of being fired because it's a great big shock and they don't know what steps to take. I've seen people in industry as well as academia who've been fired, who then agree to have a phone call with HR that isn't recorded, where there's no record of what was said on either side, and it turns into my word against yours. That's dumb. Don't do this. Everything goes by email. Everything, there is a record after, because you don't know what's going to happen. Maybe it's going to work out, maybe it's not, but you can no longer take that risk. These are the things. Yeah. Go ahead, please, Jillian.
I was just going to say, I talk to people about this all the time. It's so important to learn to be an advocate for your own career. I've seen people's careers blow up through no fault of their own, through fault of their own, through something that I think was purely preventable. I've seen, projects kind of go to the wayside. I've been on projects where I've, just kind of just sort of quietly left because I didn't like what was going on. All these kind of things are very, very important skills. And, I always like to harp on the fact we have technical problems. We have way more people problems. And just for the kind of +1, for the, learning the social skills, I've had projects just kind of nicely wrapped and handed to me because I was just nice and talked to people. And I could be like, you know, that guy over there, he's actually way better at this thing that you need done. And they were like, no, like, no thanks, we'll come talk to you. You know, so it's genuinely a very important skill to have. And I mean, these things that you're saying about like HR, learn these kind of rules, learn the rules, learn the policies around, you know, even if you don't need it or don't think you'll need it, like different policies around leave, when you can take leave, if you have a family emergency, something like that, like go. Like, please, I cannot emphasize this enough. Go learn all this stuff. It's really, really important.
It is particularly, I'm a middle-aged straight white guy, Anglophone, economically secure, no physical disabilities, you know, history of minor episodes of depression, but nothing that couldn't fairly easily be managed. No criminal record, no substance abuse problems. You want to play privilege bingo, I get to tick all the boxes. And the skills to succeed within an organization are particularly important for people who don't have all of that privilege coming in. And they're also just as important for people who are trying to change the system. We want computational work to be more respected, more valued, for it to have a seat at the table. That means we have to change the structures that we're in. We can't just rely on those structures to serve our needs, because they clearly don't. Again, as Jillian said, a lot of people spend a few years doing computational research work and then realize that they're earning 1/2 or 1/3 of what they could earn by crossing the street and going up to industry. And that's an impossible and unfair burden for people to carry when they're starting a family, when they're caring for an elderly relative, when they would like to own a house someday. It's unreasonable. We have to learn how to play this game so that we can get the changes we need, so that we can have the careers that we want, and so that the next person can have the career that they want, even if they're not already a middle-aged straight white guy in Canada. It angers me that this game is so unfair. And I think that's a large part of why I do what I do. Yes, I'd like a better world, but mostly I'm just pissed off at the one that we've got.
I hear that.
Yeah, I hear that. I love like the general overarching idea that I've heard, this theme of fields, groups of people, subgroups sort of taking responsibility for this sort of thing internally. Like you gave the example of different fields having different standards for error bars or precision or that sort of thing. And it almost seems like right now, a lot of these different scientific fields are really leaning on computer science. Like imagine if there were a bunch of computational fields and there was one scientific methods department that everyone had to lean on, right? And it had to satisfy everyone's needs. And I feel like that's allowed a lot of these fields to treat the CS department or that sort of thing. And I just love this idea that of like having people trained in the domain, sort of teaching people in the domain, and people developing and valuing, just like they value institutional knowledge, you know, in the traditional domains by granting tenure to people who know really a lot about this subfield, to actually value this institutional knowledge about computing practices, maybe even specific HR or group management practices that are particularly valuable for that field. I think instead of sort of trying to have everything be very general, I think that's great. And I just really love how this discussion has gotten so broad. You know, this is about deploying, you know, data science, but we're really talking about deploying science, where data is a small part of that, and there are lots of other things to kind of deploy and make sure that the data is usable. And I think this is great.
Terry Pratchett was one of my favorite writers. And there's a line from one of his later books where a rebellion is brewing in the city. And an older cop is asked, you know, why are you part of this? You know, you don't seem like the sort of guy who's going to go and man the barricades for truth, justice, liberty. He says, I don't care about any of that. Right? I want to be able to get up in the morning and have a cup of tea, a slice of toast, and a hard-boiled egg. That's all I want from life. But I can't be sure I'm going to have that unless I fix all this other stuff. Right? I can't be sure there's going to be food on the table and that I'm going to be there to eat it if I'm worried about not being able to afford it because there are no jobs, or if I'm worried about, guys in brown shirts kicking in my door in the middle of the night to drag me away. I feel that if we want to do the science that we know needs to be done, we've got to fix the system that we're trying to do it in, because that's what's preventing us from making progress. We really don't need another static site generator. We really don't need any number of funky machine learning algorithms. We really don't need another programming language. We need committees whose meetings are over in 50 minutes so that somebody with back problems or somebody who's pregnant has a few minutes between meetings. And in those 50 meetings, that committee actually makes a few decisions that are pointed in the right direction. I will take that over the next million software packages. Right? And it's not where I started. When we started teaching this stuff in the 90s, we were teaching technology because that's what I thought the problem was. I now realize I thought that because it was the easy problem and I wasn't brave enough yet to tackle any of the ones that really mattered. Right? The people who have been pushing for open access have been fighting the real fight. The people who've been pushing for more equitable hiring and promotion practices have been doing a lot more for science than anybody who's writing code. And I'm not saying that from a selfless point of view. We're going to get better science if we have more and better people doing the science. Right?
I think this relates back to what you were saying, even at in the small level about testing. Like how you were teaching tests in carpentry, and like the problem wasn't like how to write them; it was like what to test.
Yep.
And I think there's been a greater recognition in your career and others about like what are the important metrics and things to test to know that a system is working. Instead of these kind of, lamppost proximity tests, like, the anecdote of like, you're trying to look for your keys, by the lamppost in the dark, because that's where the light is. And so, again, like technology is kind of like the quote unquote easy thing, but maybe we need to think more about the subtleties and the tests and in our processes and our, it requires a bit more attention. It might require a lot of domain expertise and might not be able to solve everything in one sweep. We might have to dispatch to sort of subfields to help solve their own problems in their own communities where they know their stakeholders the best. And it's harder. But I just, I agree. It's sort of worth shooting for. And it's maybe reflective that we've come a little bit far in being able to recognize these things, I guess, because we've sort of gotten past the surface level stuff.
We still don't teach it, right? If I had the energy and had already finished paying off my mortgage, I would probably right now be trying to start up something similar to software carpentry to run 2-day workshops to teach these skills, because this is the next step. Right? Yes, I think it is important to be teaching Docker and to be teaching Makefiles and continuous integration and the deployment side, the DevOps of data science. Absolutely, we need that. And I think that's what your podcast is focused on. And I think those skills are important. But there's no point knowing about the importance of antisepsis if you're being asked to do surgery in a swamp, right? There's no point having those technical skills if you're in an environment where actually using them is either impractical or unrewarded, or where it takes 5 long meetings to get agreement that we're going to put together a working group that will discuss the rules that will be used to choose the members of the committee that are going to draft the white paper to put forward options to the provost for consideration about how we might want to have some sort of a discussion group about adding more computational material to the undergraduate curriculum. And if I sound tired, it's because I am, right? We're supposed to be the smart ones. We can do this better.
Well, if you want a pep talk, I absolutely wish I had heard more career advice. I just absolutely made it up as I went along, and I had no clue what I was doing. And the fact that it has worked out is pretty much luck, like purely just luck, So if you ever want to keep on going with that.
And I think about all the people it hasn't worked out for.
Yeah, exactly. Right. That's like, I've seen so many people drop off the talent pipeline because at some point they just put their hands up and they're like, you know what, no more, I'm out.
And how it acts differentially, right? Not all people drop out at the same rate because the system excludes them at different rates. And I care about that from just a fairness point of view, but we also just can't afford to continue to throw away smart people because they didn't room with the right person at Harvard. I would say no offense to the Harvard grads on this call, but I don't care.
So we're So we're at the hour, and I want to be respectful of your time, Greg. Although we love listening to you. Maybe if you want to send us off with anything you'd like to leave us with about
sure,
really anything.
Sure. If people want a place to start, I've been ranting, I've been diagnosing the problem. If you want to know what to do next, Michael Jacoby Brown's book, Building Powerful Community Organizations, is one very good place to start because he's been doing it for 50 years. The Manson Rising book, Fearless Change, it's an unfortunate title and you can skip the first 20 pages. It's the usual self-congratulatory airport business book kind of stuff, but it's then a catalog of design patterns for getting change in organizations. What can you do? At what point do you try particular techniques? How do you tell if it's working? There's nothing in there that will really surprise you, but that's not the same as saying you would have thought of it all by yourself. And they organize the patterns temporally. Here's the things you do when you're trying to find out if there's any traction at all. Here's what you do to get your first few supporters, and so forth. And I found that one really helpful. And finally, Stephen Brookfield's book, The Discussion Book, is another really useful catalog. It is 50 different ways that groups of people can have a productive discussion when they need to share information or reach a decision. Of those 50 techniques, I had seen about 15 before I read the book. And I think I know this stuff reasonably well, but I'd never gone off and looked to expand my repertoire. And of those 50 techniques, I've only ever seen 5 or 6 implemented in software, right? Slack is just IRC, is just the old Unix talk utility, but with more emoji and a 400 megabyte installer. Right? There's nothing really new there. We just keep dressing up the old ideas. There are so many other really good ideas we could use to be more efficient and more equitable, which turn out to be the same thing, when we're trying to have group discussions. I don't use all 50, but it certainly helped me be better and have more tools in my toolbox for when I need them. So I think those are 3 really good places for people to start. I highly recommend Carl Fogel's book on producing open source software if you are running any sort of research software project, open source or not. You're going to have to deal with all of the issues he discusses, and he's been doing this a long time, longer than I have. So lots of good advice in that for people as well. And as I said, I'm starting to put together workshops on this. Go to codebender.org. You'll see what I currently think I can teach in 2 days. I'm not going to be able to fit it all in, but if people have suggestions about what else ought to be there, what else they really need to know, I'll see what I can put together.
That's fantastic, Greg. Yeah, I mean, it reminds me a little bit about techniques I've encountered in like machine learning, active learning. Like there's uncertainty sampling versus diversity sampling. Like what you know you don't know, and what you don't know you don't know. And this has been I think a master class in like things you maybe don't know that you don't know, and resources where you can find out more. And I love what you said about we've got all the future we need to share it better. And just I think it's great having you on to you know, to just help out our listeners and everyone to kind of explore more and see what we have better.
Glad to be useful. As I've said to people, I'm absolutely not a thought leader. I'm more of a thought raccoon. You know, I go and poke around and fish things out and put them together. But I think that's a useful role as well. I think there's so much that we already know. We just need to put the pieces together and put them in front of people. And it turns out you don't have to learn that much to do better. And it's kind of fun.
Great, thanks.
Yeah, this is
Jillian, do you want to
great.
take us away?
Yeah, sure. So I've been taking notes and on the books and the other resources that you mentioned, and so those will be in the show notes, which I tend to update after I press the end broadcast button so that I can go and type them in there. So they will be in there very soon. And thank you so much for coming on the show, and it was a really great and interesting discussion.
Pleasure to meet all of you.
Greg.
All right.
Thank you all very
that's
much.
It. Thank
Bye.
you. Next week, guys.
Take care.
Bye-bye.
Have a good week.
Take care.
You too.